On July 1st, 2025, at precisely 14 hours 37 minutes Universal Time, the Atlas Survey telescope in Chile detected something that made its operators question their instruments. The automated system had flagged an object moving against the star field at 4.5 astronomical units from the Sun, roughly the distance of Jupiter's orbit. But the mathematics emerging from the detection algorithms suggested something that violated every expectation astronomers held about objects at that distance. The velocity calculations were the first sign something was fundamentally wrong. Objects in our solar system follow predictable patterns, bound by the Sun's gravity into elliptical orbits that have been understood since Kepler's time. Even the most eccentric comets from the Oort cloud, that distant sphere of icy bodies surrounding our solar system, move according to these ancient laws. But this object, initially designated C/2025N1, was traveling at speeds that made no sense for something that belonged here. Within 6 hours of discovery, 3 independent observatories had confirmed the impossible. The object's trajectory showed an orbital eccentricity of 1.47, far exceeding the value of 1 that marks the boundary between bound and unbound orbits. This wasn't just passing through our solar system, it was screaming through at velocities that suggested it had never been gravitationally bound to our Sun at all. The realization sent a chill through the astronomical community that had nothing to do with the Chilean winter night. The discovery shouldn't have happened when it did. Statistical models suggested interstellar objects of this size should be detected much closer to the Sun, where their smaller profiles become visible to our instruments. Finding 3I Atlas at such a vast distance implied either extraordinary luck or something about this object that made it unusually bright for its size. Neither explanation satisfied the growing number of scientists joining emergency video conferences that night. Dr. Elena Rodriguez at the European Southern Observatory was among the first to articulate what others were thinking but hesitant to voice. The detection parameters suggested this object had been visible for weeks, possibly months, before the automated systems flagged it. How had every survey missed something moving this fast? The only explanation was that it had recently brightened, activating at a distance where frozen volatiles should remain locked in cosmic deep freeze. The initial spectroscopic observations added another layer of unease. The fuzzy coma surrounding the nucleus, that characteristic cloud of gas and dust that defines a comet, was present but wrong. The spectral signatures didn't match the familiar patterns of water-ice sublimation that dominated every comet in our catalogue. Instead, the infrared detectors were registering something else entirely, emissions that would later be identified as carbon dioxide, in proportions that challenged fundamental assumptions about planetary formation. By dawn in Chile, as the telescope closed its dome against the rising sun, 3I Atlas had already earned its designation as the third confirmed interstellar object to visit our solar system. But unlike its predecessors, Oumuamua and Borisov, this visitor arrived with characteristics that seemed designed to challenge every model astronomers had carefully constructed about how celestial objects should behave. The discovery timing itself carried an uncomfortable precision. Earth's most advanced telescopes had just completed major upgrades. The James Webb Space Telescope was perfectly positioned for infrared observations. The global astronomical community was better prepared than ever to study an interstellar visitor. It was as if 3I Atlas had waited for humanity to be ready to observe it, arriving at the perfect moment to maximize our ability to witness its passage. This thought, irrational as it seemed, would only grow stronger as more data arrived in the coming weeks. The number appeared on screens across the global astronomical network with a stark simplicity that belied its profound implications. 209,000 kilometers per hour. In the language of orbital mechanics, this translated to a heliocentric velocity that placed 3I Atlas in a category entirely its own. This wasn't just fast by cosmic standards, it was the fastest interstellar object humanity had ever detected, moving at speeds that raised fundamental questions about how such velocities could be achieved and maintained across interstellar distances. To grasp the true magnitude of this speed, consider that a rifle bullet travels at roughly 1,200 kilometers per hour. 3I Atlas was moving 170 times faster than that bullet, carrying kinetic energy that spoke of violent origins or mechanisms beyond conventional understanding. The Voyager spacecraft, humanity's fastest interstellar probes, crawl through space at a mere 62,000 kilometers per hour. This visitor from another star system was lapping our greatest achievements in space exploration 3 times over. Dr. Michael at MIT's Kavli Institute ran the calculations repeatedly, hoping to find an error that would bring the velocity down to something more reasonable. But the astrometric data from multiple observatories aligned perfectly. The object's hyperbolic excess velocity, the speed it would maintain even after escaping the sun's gravitational influence entirely, stood at 61 kilometers per second. This wasn't just passing through. It was racing through our solar system as if fleeing from something or towards something with an urgency that defied natural explanation. The velocity raised immediate questions about origin and ejection mechanisms. Natural processes that could accelerate rocky or icy bodies to such speeds were limited and violent. A close encounter with a stellar binary system might provide the gravitational slingshot needed. A supernova explosion could theoretically launch debris at these velocities. But each scenario required specific conditions that were statistically improbable, and none fully explained the maintained structural integrity of an object that showed clear signs of volatile activity. Previous interstellar visitors had already stretched our understanding of natural velocities. Oumuamua traveled at 26 kilometers per second relative to the local standard of rest. Borisov managed 32 kilometers per second, but 3I Atlas nearly doubled these already impressive speeds, suggesting either an origin story of unprecedented violence or acceleration mechanisms that transcended simple gravitational interactions. The trajectory analysis revealed another troubling detail. The velocity vector didn't point back toward any obvious stellar association or recent supernova remnant. Instead, it suggested an origin in the thick disk population of the galaxy, among stars that formed 8 to 12 billion years ago when the universe was less than half its current age. If 3I Atlas had been traveling at its current velocity since ejection, the journey time implied origins before our solar system even existed. Energy considerations made the velocity even more puzzling. Maintaining such speed across interstellar distances meant surviving countless gravitational perturbations from stars, molecular clouds, and dark matter concentrations. Each encounter should have altered the trajectory, gradually randomizing the velocity vector. Yet 3I Atlas arrived in our solar system with a velocity that seemed precisely maintained, as if protected from these disruptions or continuously corrected throughout its journey. Some researchers began calculating alternative acceleration scenarios. Could magnetic fields in interstellar space provide additional acceleration? Might radiation pressure from multiple stellar sources compound over millions of years? Each hypothesis struggled against the magnitude of the observed velocity. The energy required to accelerate even a small comet nucleus to such speeds exceeded what natural processes could reasonably provide. The velocity of 3I Atlas forced astronomers to confront an uncomfortable possibility. Either the universe contained natural acceleration mechanisms we didn't understand, or this object's speed resulted from something other than natural processes. Neither option was particularly comforting to scientists who had spent careers believing they understood the fundamental forces that govern celestial motion. The James Webb Space Telescope's near-infrared spectrograph delivered its verdict on August 6, 2025, in the form of spectral lines that made no sense according to everything astronomers thought they knew about comet composition. The data showed carbon dioxide emissions dominating the spectrum with a CO2 to water ratio of 8:1. In the carefully controlled language of scientific papers, this was described as unprecedented. In the private conversations between researchers, it was called impossible. Every comet in our solar system, from the periodic visitors like Halley to the long-period wanderers from the Oort cloud, shows water ice as its primary volatile component. Typical comets display water to CO2 ratios ranging from 10:1 to 100:1. Water is the fundamental building block of cometary ice, the substance that defines these ancient remnants of planetary formation. To find a comet where carbon dioxide dominated by such an extreme margin was like finding an ocean made primarily of sand. Dr. Sarah Kim at the Space Telescope Science Institute reviewed the spectroscopic data with growing disbelief. The carbon dioxide signature was unambiguous, showing up in multiple wavelength bands with signal strength that ruled out instrumental error. But the water signature that should have dominated the spectrum was barely detectable, appearing only as faint traces that required sophisticated analysis to confirm. This wasn't just unusual, it violated the basic chemistry models of how icy bodies form in protoplanetary disks. The discovery sparked immediate theoretical scrambling among planetary scientists. In a typical protoplanetary disk, water ice condenses at temperatures below 150 Kelvin, forming the bulk of volatile material in the outer regions where comets originate. Carbon dioxide requires even colder temperatures, condensing only below 70 Kelvin. The temperature gradient in a forming planetary system naturally produces more water ice than CO2 ice, a ratio that should be preserved in any comet, regardless of its origin. But 3I Atlas seemed to mock these theoretical constraints. Its extreme CO2 dominance suggested formation in an environment unlike anything in our solar system's history. Perhaps it originated near a CO2 snowline in another star system, in a narrow zone where carbon dioxide could condense, but water remained vaporized. Or maybe it formed in a region where the initial nebula composition was radically different from our own, enriched in carbon and depleted in water through processes we couldn't imagine. The extended nature of the carbon dioxide emission added another layer to the mystery. The SPIREX mission's wide-field infrared mapping revealed that the CO2 cloud extended at least 348,000 kilometers from the nucleus. This was nearly the distance from Earth to the Moon, an enormous volume of gas that a nucleus only a few kilometers across shouldn't be able to sustain. The physics of sublimation suggested that such a small body should produce a compact coma, not this vast envelope of carbon dioxide that seemed to defy the inverse square law of gas expansion. Laboratory experiments with CO2 ice analogues couldn't reproduce what 3I Atlas was displaying. When researchers subjected carbon dioxide ice to conditions mimicking the solar radiation at 3I Atlas's distance, the sublimation rates were orders of magnitude too low to explain the observed emission. Either the object contained far more CO2 than its size allowed, or the sublimation was being enhanced by mechanisms that transcended simple solar heating. The isotopic ratios in the carbon dioxide, if they could be measured with sufficient precision, might reveal the stellar environment where 3I Atlas formed. Different types of stars produce different carbon isotope ratios through their nuclear fusion processes. But the technical challenges of measuring isotopes in such a faint, distant object pushed current instruments to their limits. The preliminary attempts suggested ratios that didn't match any stellar population models, adding another data point to the growing collection of anomalies. As August progressed toward September, the carbon dioxide mystery deepened rather than resolved. Each new spectrum confirmed the extreme CO2 dominance, while offering no explanation for how such chemistry could arise naturally. The universe had delivered a comet that shouldn't exist according to our understanding of chemistry and physics. The orbital mechanics of 3I Atlas contained a geometric precision that made seasoned astronomers uncomfortable in ways they struggled to articulate. As trajectory specialists at NASA's Jet Propulsion Laboratory refined their calculations with each new positional measurement, a pattern emerged that seemed less like cosmic coincidence and more like careful navigation. The path this interstellar visitor followed through our solar system threaded between planetary orbits with a precision that defied statistical probability. Dr. Amanda Foster, who had spent 2 decades modeling asteroid trajectories for planetary defense, first noticed the anomaly in early August. The perihelion point, 3I Atlas's closest approach to the Sun, would occur at 0.87 astronomical units, placing it perfectly between the orbits of Earth and Mars. But it wasn't just the distance that troubled her, it was the timing. The object would reach this point when Earth was positioned on the opposite side of the Sun, hidden behind our star's glare at the moment of maximum activity. The approach vector added another layer of unsettling precision. 3I Atlas entered our solar system from a direction that minimized gravitational perturbations from the gas giants while maximizing the observation window from Earth during its inbound journey. Jupiter, whose massive gravity typically deflects or captures incoming objects, was positioned in its orbit such that its influence on 3I Atlas was minimal. Saturn, Uranus, and Neptune were similarly arranged in configurations that provided clear passage for this visitor. Statistical analysis of the trajectory revealed probabilities that strained credibility. The chance of a random interstellar object following this particular path through our solar system was calculated at roughly 1 in 50 million. This assumed natural processes and random approach angles based on the expected distribution of interstellar debris. Either 3I Atlas represented an extraordinary statistical outlier, or its trajectory wasn't entirely natural. The orbital plane orientation provided another curious detail. Most interstellar objects should approach from random angles relative to the ecliptic, the plane in which planets orbit. Oumuamua had arrived from well above the ecliptic. Borisov came in at a steep angle. But 3I Atlas entered nearly parallel to the planetary plane, maximizing its time in the region where Earth-based telescopes routinely scan for asteroids. It was as if the object wanted to be discovered. Perturbation analysis revealed that 3I Atlas's trajectory showed remarkable stability despite passing through regions of complex gravitational fields. Small objects are typically buffeted by the competing pulls of planets, the Sun, and even large asteroids. These forces create measurable deviations from simple hyperbolic paths, but 3I Atlas maintained its trajectory with a precision that suggested either unusual mass distribution or active course corrections too subtle for current detection methods. The closest approach to Earth, scheduled for December 2025 at 1.88 astronomical units, would occur when the object was positioned optimally for spectroscopic observation from both ground and space-based telescopes. The geometry would provide perfect phase angles for studying surface composition while maintaining a safe distance that posed no impact threat. It was the ideal flyby distance for scientific study, close enough for detailed observation, but far enough to eliminate any danger. Reverse trajectory modeling attempted to trace 3I Atlas back to its origin point, but the results only deepened the mystery. The path didn't point toward any particular star or stellar association. Instead, it suggested origins in empty space between stellar systems, as if the object had been traveling on this precise trajectory for millions of years, aimed at our solar system long before humans evolved to observe it. Some researchers began examining whether gravitational lensing or three-body interactions could naturally produce such trajectories. Complex models involving multiple stellar encounters were constructed, trying to find natural scenarios that could result in the observed path. Each model required increasingly unlikely coincidences, stacking improbabilities until the natural explanation became more extraordinary than alternatives no one wanted to seriously consider. The trajectory of 3I Atlas represented more than just orbital mathematics. It was a path that maximized human observation while minimizing gravitational disruption, arriving at the perfect time with the perfect approach angle. In the quiet offices where orbital dynamicists worked through their calculations, an unspoken question lingered. What if this trajectory wasn't accidental? The number stared back from computer screens at the SpaceX Mission Control Center with an almost mocking simplicity. 348,000 kilometers. That was the measured extent of the carbon dioxide cloud surrounding 3I Atlas, a volume of gas so vast it could swallow the entire Earth-Moon system with room to spare. For a nucleus estimated at no more than 5.6 kilometers across, this represented an emission region that violated every model of cometary outgassing that astronomers had carefully constructed over decades of observation. Dr. Jennifer Walsh at Caltech had analyzed hundreds of comets throughout her career, mapping their comas with infrared spectroscopy that could trace gas molecules across vast distances. But nothing in her experience prepared her for the SpaceX data streaming in during August 2025. The carbon dioxide emission didn't follow the inverse square law that governed gas expansion in vacuum. Instead of diminishing rapidly with distance from the nucleus, the CO2 maintained detectable densities across a region that should have been empty space. The physics of the situation demanded extraordinary explanations. A typical comet nucleus of 3I Atlas's size, even one composed entirely of carbon dioxide ice, couldn't sublimate fast enough to maintain such an extensive gas cloud. The energy required would exceed what solar radiation could provide at that distance. The mathematics were unforgiving. Either the nucleus was orders of magnitude more active than any comet ever observed, or additional sources were contributing to the emission. Laboratory simulations attempted to reproduce the phenomenon using CO2 ice samples under conditions matching 3I Atlas's solar distance. The results were unanimous in their failure. Even under the most favorable assumptions about surface area and sublimation efficiency, the models produced gas clouds barely 1/10 the observed size. The discrepancy wasn't a minor error that could be explained by measurement uncertainty. It was a fundamental violation of thermodynamic principles. The fragmentation hypothesis emerged as one potential explanation. Perhaps 3I Atlas wasn't a single solid nucleus, but a collection of smaller fragments, each contributing to the total gas emission. This would effectively multiply the surface area available for sublimation, potentially explaining the vast CO2 cloud. But high-resolution imaging from Hubble showed no evidence of multiple components. The light source remained stubbornly singular, a point of brightness that refused to resolve into separate pieces. Another theory proposed that 3I Atlas had experienced a massive outburst event, releasing enormous quantities of CO2 in a single explosive episode. Such events had been observed in other comets, usually triggered by the sudden exposure of fresh, volatile, rich material. But the steady nature of the emission argued against this scenario. The cloud wasn't expanding and dissipating as expected from a single release. It was being continuously maintained at impossible levels. The geometric distribution of the gas added another puzzle. Instead of forming a symmetric sphere around the nucleus, the CO2 cloud showed subtle asymmetries that suggested directional emission. But the patterns didn't match simple models of solar-driven sublimation. The gas seemed to flow in preferential directions that had no obvious correlation with solar heating, gravitational gradients, or the object's motion through space. Some researchers began exploring whether electromagnetic effects could explain the extended emission. If the CO2 molecules were becoming ionized by solar ultraviolet radiation, they might interact with the solar magnetic field in ways that prevented normal dispersal. But the ionization rates at 3I Atlas's distance were too low to significantly affect such a massive volume of gas. The mechanism, if it existed, would require physics beyond current understanding. The temporal evolution of the cloud provided the final, unsettling detail. As 3I Atlas approached the Sun, the emission region should have grown proportionally with increased heating. Instead, it maintained remarkable stability, neither expanding nor contracting significantly, despite changing solar radiation. It was as if something was regulating the gas release, maintaining the cloud at a specific size, regardless of external conditions. The Hubble Space Telescope represented humanity's finest eye on the cosmos, a precision instrument that had revealed the births of stars and the deaths of galaxies. Yet when it turned toward 3I Atlas in July 2025, this technological marvel encountered something that reduced it to expensive impotence. Despite multiple observations with exposure times pushed to their practical limits, Hubble could not resolve the nucleus of our interstellar visitor. The solid heart of 3I Atlas remained hidden, a point source stubbornly refusing to reveal its true nature. Dr. Robert Martinez, who had used Hubble to study dozens of comets over his career at the Space Telescope Science Institute, found himself staring at images that defied explanation. The telescope's resolution should have been sufficient to detect surface features on an object of 3I Atlas's estimated size at its current distance. Previous comets had revealed their nuclear shapes, rotation states, and even active regions where jets of gas erupted from specific locations. But 3I Atlas offered only a bright central point surrounded by its enigmatic coma. The size constraints derived from Hubble's non-detection were themselves troubling. The nucleus had to be smaller than 5.6 kilometers to remain unresolved, yet it had to be large enough to produce the observed brightness and activity. This narrow range created a paradox. Too small, and the object couldn't generate enough gas to sustain its enormous CO2 cloud. Too large, and Hubble should have resolved its shape. 3I Atlas seemed to exist in an impossible sweet spot that challenged both extremes. The rotation state represented another invisible mystery. Every small body in the solar system rotates, their spin states induced by formation processes and subsequent collisions. This rotation creates periodic brightness variations as different faces of irregular objects face the Sun and Earth. Astronomers use these light curves to determine rotation periods, axis orientations, and even surface properties. But 3I Atlas showed no such variations. Its brightness remained eerily constant across weeks of observation. 3 explanations competed for acceptance, each carrying its own unsettling implications. First, the object might be rotating very slowly, with a period so long that months of observation hadn't captured a complete cycle. But such slow rotation would be unusual for an active comet experiencing asymmetric outgassing forces. Second, it might be rotating with its axis pointed directly at Earth, eliminating the cross-sectional changes that create brightness variations. The odds of such perfect alignment were astronomically small. Third, and most troubling, the nucleus might be nearly spherical with uniform surface properties, a geometry that nature rarely produces. Advanced image processing techniques pushed Hubble's data to its absolute limits, searching for any hint of structure within the bright central region. Deconvolution algorithms attempted to sharpen the point spread function. Lucky imaging selected the moments of best atmospheric stability. Drizzle techniques combined multiple observations to enhance resolution. Yet the nucleus remained obstinately hidden, as if wrapped in its own luminous cocoon that no amount of digital enhancement could penetrate. The photometric properties added layers to the mystery. The color indices measured by Hubble suggested a surface that was neither purely icy nor obviously rocky. The spectral slope in visible wavelengths indicated moderate reddening, consistent with organic compounds or processed materials, but without resolved surface features. Determining whether this represented uniform composition or localized regions of different materials remained impossible. The inability to detect jets or active regions was particularly frustrating. Cometary activity typically originates from specific locations where subsurface volatiles find pathways to escape. These jets create coma asymmetries and dust patterns that reveal nuclear rotation and surface geology. But 3I Atlas's coma appeared remarkably symmetric in Hubble's images, as if the entire nucleus was uniformly active, or the activity was somehow regulated to prevent the formation of discrete jets. Comparison with previous interstellar visitors heightened the frustration. Oumuamua, despite showing no coma, had revealed its elongated shape through rotational light curves. Borisov had displayed typical cometary morphology with clear nuclear condensation and jet structure. But 3I Atlas seemed designed to frustrate observation, active enough to hide its nucleus, but not active enough to reveal the patterns that would explain its behavior. The Swift Observatory's ultraviolet optical telescope detected them clearly in late July 2025. Hydroxyl radicals, the OH molecules that form when solar ultraviolet radiation breaks apart water molecules in a comet's coma. It was textbook cometary chemistry, the signature that had confirmed water ice in hundreds of comets throughout our solar system. Dr. Lisa at NASA's Goddard Space Flight Center logged the detection with satisfaction. Finally, something about 3I Atlas that made conventional sense, but that satisfaction would prove premature. When the SphereX mission turned its infrared spectrometers toward 3I Atlas in early August, searching for the direct spectral signatures of water vapor that should accompany hydroxyl production, the results were bewildering. The water signal was barely above the detection threshold, so weak that it required sophisticated statistical analysis to confirm its presence. The abundance was at least an order of magnitude below what the hydroxyl measurements predicted. It was as if the water was being created and destroyed through pathways that bypassed normal sublimation. The discrepancy between hydroxyl detection and water non-detection created a chemical paradox that had no precedent in cometary science. Hydroxyl radicals in comet comas originate almost exclusively from water photodissociation. The process is simple and well understood. Water molecules sublime from ice. Solar UV breaks the H2O into H and OH, and both products become detectable in their characteristic wavelengths. Finding abundant OH without corresponding water vapor was like finding smoke without fire. Dr. Michael Petrov at the European Space Agency proposed that 3I Atlas might contain water ice trapped beneath an insulating crust that prevented efficient sublimation. In this scenario, only small amounts of water vapor could escape through cracks or thin regions, but once in the coma, UV radiation would still produce the observed hydroxyl. The model was mathematically consistent, but required surface properties unlike any comet previously studied. The temperature profile of 3I Atlas added another complication. At its distance from the Sun during the observations, water ice sublimation should have been relatively inefficient compared to more volatile substances like carbon dioxide. But even accounting for temperature effects, the water detection was anomalously low. The nucleus seemed to be selectively releasing CO2 while holding its water in a frozen grip that defied thermodynamic expectations. Laboratory experiments with mixed ices attempted to reproduce the observed chemistry. When CO2 and water ice were combined in various ratios and exposed to conditions simulating 3I Atlas's environment, the water always sublimated along with the carbon dioxide. No combination of pressure, temperature, or composition could create the extreme selective sublimation that the observations demanded. The physics insisted that water should be there, but the spectra insisted it wasn't. Alternative hydroxyl production mechanisms were explored with increasing desperation. Could the OH radicals come from something other than water? Some metal oxides could theoretically produce hydroxyl when exposed to solar wind particles. Certain organic compounds might photodissociate into OH-bearing fragments. But each alternative required concentrations or processes that seemed even more unlikely than the missing water itself. The spatial distribution of hydroxyl provided another clue that deepened rather than resolved the mystery. The OH emission extended well beyond the visible coma, forming a hydrogen cloud detected by ultraviolet telescopes that reached distances where no parent molecules should survive. The extended hydrogen suggested water was present somewhere in the system, but in a form or location that remained invisible to direct detection. Some researchers began considering whether 3I Atlas represented an entirely new class of cometary object, one where water existed in exotic phases or chemical combinations that behaved differently from conventional ice. Perhaps the extreme age and interstellar processing had created water-bearing minerals that released hydroxyl through surface chemistry rather than sublimation. But such mechanisms were purely theoretical, unsupported by any laboratory evidence. The missing water problem epitomized the frustration of studying 3I Atlas. Every measurement that should have provided clarity instead added complexity. The object seemed to follow chemical rules just closely enough to remain recognizable as a comet, but deviated in ways that suggested either unknown physics or chemistry evolved in an environment utterly unlike our solar system. The arrival of 3I Atlas in July 2025 carried a temporal precision that made statistical astronomers reach for increasingly unlikely explanations. Dr. James Thompson at Carnegie Observatories had run the probability calculations dozens of times, each iteration confirming what seemed impossible to accept. The odds of an interstellar object arriving at this particular moment, with these particular characteristics, visible to these particular instruments, stretched credibility beyond the breaking point of coincidence. Consider the cosmic timing. The Vera Rubin Observatory, humanity's next-generation survey telescope, designed specifically to detect faint, fast-moving objects, was scheduled to begin operations in late 2025. The James Webb Space Telescope had just completed its commissioning phase and was operating at peak efficiency. The global network of ground-based observatories had never been more sophisticated or better coordinated. 3I Atlas arrived at the precise historical moment when human civilization possessed the maximum capability to study it. The orbital geometry added another layer of suspicious precision. The object's trajectory brought it through the inner solar system during a narrow window when Mars, Earth, and the outer planets were positioned to provide multiple observation angles. The Mars flyby on October 3rd would occur when the red planet's orbital assets were optimally positioned. The December Earth approach would happen when both professional and amateur astronomers in the Northern Hemisphere had long winter nights for observation. But the most unsettling aspect was the solar conjunction timing. Just as 3I Atlas reached perihelion, the moment of maximum activity when its unusual chemistry would be most dramatically expressed, Earth would be positioned on the opposite side of the Sun. For approximately 60 days, from late September through November, the object would be completely unobservable from our planet. It was as if the universe had arranged a cosmic curtain to fall at the climax of the performance. Dr. Rebecca Foster at Oxford had studied the distribution of discovery times for various classes of astronomical objects. Supernovae were detected randomly throughout the year. Asteroid discoveries followed seasonal patterns related to weather and sky darkness. But interstellar objects showed no predictable pattern, until now. The progression from Oumuamua in 2017 to Borisov in 2019 to 3I Atlas in 2025 suggested an acceleration in discovery rate that exceeded what improved survey capabilities could explain. The technological coincidences accumulated beyond statistical comfort. SphereX, the mission that would map 3I Atlas's enormous CO2 cloud, had launched just months before the discovery. The European Space Agency's Enhanced Tracking Network had come online in early 2025. China's Fast Radio Telescope had recently completed upgrades that would have detected any electromagnetic emissions from the visitor. Every tool needed to study this object had been positioned and prepared as if by schedule. Some researchers attempted to explain the timing through anthropic reasoning. Perhaps many interstellar objects had passed through our solar system undetected, and we only noticed 3I Atlas because our technology had finally reached the necessary sophistication. But this explanation faltered against the object's unusual brightness and activity. 3I Atlas wasn't marginally detectable. It was surprisingly obvious once discovered, as if it had chosen to announce itself. The discovery circumstances themselves defied expected patterns. The Atlas survey system that found 3I Atlas was designed to detect near-Earth asteroids, not interstellar visitors at Jupiter's distance. The object appeared in a region of sky that wasn't particularly favorable for detection, yet the automated algorithms flagged it immediately, as if its unusual motion was deliberately crafted to trigger detection systems designed for entirely different purposes. Historical analysis revealed an uncomfortable pattern. Each interstellar visitor had arrived with characteristics that pushed the boundaries of human observation capabilities at that specific time. Oumuamua challenged our ability to track fast-moving objects. Borisov tested our chemical analysis capabilities. 3I Atlas seemed designed to explore the absolute limits of what current technology could observe and measure, arriving just as those limits reached their maximum extent. The psychological impact on the astronomical community was profound, but rarely discussed in published papers. The timing felt intentional, choreographed, as if 3I Atlas was less a random visitor and more a scheduled examination of human capabilities. The thought was unscientific, irrational, yet it persisted in quiet conversations between observers during long nights at telescopes, watching this impossible object race toward its hidden perihelion performance. The progression from Oumuamua to Borisov to 3I Atlas reads like a carefully orchestrated crescendo of cosmic strangeness, each visitor more mysterious than the last, each one violating different fundamental assumptions about how interstellar objects should behave. Dr. Karen Mitchell at Harvard Center for Astrophysics had studied all three visitors intensively, and her comparative analysis revealed a pattern that made her increasingly uncomfortable with each passing month of observations. Oumuamua had arrived in 2017 like a silent herald, tumbling through our solar system with no visible coma, no detectable outgassing, yet somehow accelerating away from the sun through forces that defied conventional explanation. Its elongated shape, with an aspect ratio of at least 6:1, possibly as high as 10:1, represented a geometry that gravitational forces should have destroyed eons ago. The acceleration anomaly of roughly 10 to the -5 meters per second squared might seem tiny, but it was real, measured, and inexplicable through normal cometary physics. 2 years later, Borisov appeared as if to reassure the astronomical community. Here was a proper interstellar comet, complete with a visible coma, a prominent tail, and spectroscopic signatures that, while unusual, at least fit within the framework of known chemistry. Its carbon monoxide excess was remarkable, but not impossible. The object followed predictable trajectories without mysterious accelerations. Scientists breathed a collective sigh of relief. Perhaps Oumuamua had been the anomaly, not the rule. Then 3I Atlas arrived in 2025, and any comfort derived from Borisov evaporated like its own sublimating ices. This visitor seemed designed to combine the worst anomalies of its predecessors while adding entirely new categories of impossibility. It had a coma like Borisov, but one that extended to physically impossible distances. It showed no acceleration anomaly like Oumuamua, yet its chemistry defied every model of natural formation. Each measurement added another violation of expected behavior. The escalation pattern was what troubled researchers most deeply. It wasn't just that these objects were different from each other. They were progressively more challenging to explain through natural processes. Oumuamua's mysteries were primarily mechanical. Unusual shape, unexplained acceleration. Borisov's were chemical. Strange but not impossible molecular ratios. 3I Atlas combined mechanical, chemical, and thermodynamic impossibilities into a single package that pushed against the boundaries of known physics. Dr. Mitchell's statistical analysis revealed something even more unsettling. The probability of detecting these three specific objects in this specific order was vanishingly small. If interstellar space contained a random distribution of natural debris, we should have detected the most common types first. Instead, we had discovered three radically different objects, each one seemingly designed to challenge different aspects of our understanding. It was as if someone was sending increasingly complex puzzles, testing the limits of human scientific capability. The discovery rates themselves formed a suspicious pattern. The gap between Oumuamua and Borisov was 2 years. Between Borisov and 3I Atlas, 6 years. If the pattern held, the next visitor should arrive around 2035, giving humanity a decade to develop new observational capabilities. Some researchers had begun calling this the examination hypothesis in private discussions, though none would publish such speculation in peer-reviewed journals. Each visitor had also demonstrated different aspects of what interstellar objects could be. Oumuamua showed that they could be rocky or metallic, possibly fragments of destroyed planets. Borisov proved they could be icy, carrying frozen samples of alien chemistry. 3I Atlas suggested they could be something else entirely, objects that transcended simple categories of rock or ice, exhibiting behaviors that required new physics to explain. The chemical progression was particularly striking. No detectable volatiles, then carbon monoxide excess, then carbon dioxide dominance. Each step represented a different formation temperature, a different stellar environment, a different set of physical conditions. Together, they painted a picture of galactic diversity that was simultaneously exciting and terrifying. If three objects could be this different, what else was wandering between the stars? The kinematic analysis placed 3I Atlas's origin among the galaxy's most ancient stellar population, and the implications sent a chill through the community of astronomers who understood what this truly meant. Dr. Alexander Volkov at the Max Planck Institute for Astronomy had traced the visitor's trajectory backward through time, accounting for gravitational perturbations and galactic rotation, arriving at a conclusion that transformed 3I Atlas from a curiosity into something far more unsettling. The thick disk population formed between 8 and 12 billion years ago, during an epoch when the Milky Way was young and violent, still recovering from massive merger events that had shaped its structure. These stars were born from gas clouds with different chemical compositions than our Sun's birthplace, depleted in heavy elements, enriched in primordial hydrogen and helium. If 3I Atlas originated in this environment, it predated not just Earth, but the entire solar system by billions of years. The age implications were staggering. This object had been wandering the galaxy since before the Sun ignited, before the planets formed, before the chemical elements necessary for life as we know it had been fully synthesized in stellar furnaces. It had survived the deaths of the stars that created it, witnessed the birth and evolution of countless planetary systems, and somehow maintained its structural integrity across temporal scales that reduced human civilization to less than a rounding error. But the thick disk origin carried darker implications that most papers carefully avoided discussing. Stars from this population had experienced the galaxy's most violent epochs, when collision rates were higher, when supernovae were more frequent, when the radiation environment would have been lethal to any nascent life. If 3I Atlas formed in such conditions, what kind of chemistry could survive? What processes could create the impossible CO2 dominance we observed? Dr. Volkov's model suggested 3I Atlas had traveled at least 100,000 light-years during its journey, assuming constant velocity since ejection. But constant velocity was itself an impossibility. Every stellar encounter should have altered its trajectory. Every passage through a molecular cloud should have affected its speed. The fact that it arrived in our solar system with such precise targeting suggested either extraordinary luck or trajectory maintenance through unknown mechanisms. The preservation state of 3I Atlas defied every model of interstellar medium erosion. Cosmic rays should have processed its surface materials into an amorphous crust. Micrometeorite impacts should have gardened its outer layers into well-mixed regolith. Thermal cycling from stellar encounters should have fractured any coherent structure. Yet this ancient wanderer was actively outgassing, releasing pristine volatiles as if freshly formed. The isotopic implications were equally troubling. Different stellar populations produce different isotope ratios through their nucleosynthesis processes. If 3 Eatlas truly originated in the thick disk, its isotopes should reflect the primitive conditions of the early galaxy. Preliminary attempts to measure these ratios had produced results that didn't match any stellar evolution models, as if the object contained materials that couldn't have formed through known nuclear processes. Some researchers had begun calculating the probability that 3 Eatlas had been deliberately preserved rather than naturally surviving its eons-long journey. The energy requirements for maintaining structural integrity across such timescales exceeded what passive materials could provide. Either the object possessed self-repair mechanisms, or it had been protected by technologies that transcended current understanding. Neither possibility was comforting. The temporal paradox was inescapable. If 3 Eatlas was truly ancient, it should be dead, inert, a frozen relic barely distinguishable from the cosmic background. Instead, it blazed with activity, its enormous CO2 cloud proclaiming vitality that should have been exhausted billions of years ago. It was as if the object existed outside normal temporal constraints, maintaining its youth through mechanisms that violated thermodynamic laws. The thick disk origin also implied that 3 Eatlas had witnessed cosmic evolution on scales humans could barely comprehend. It had existed when the universe was less than half its current age, when galaxies were still assembling, when the cosmic web was young. Whatever information this object carried, it came from an epoch so removed from current conditions that our physics might not fully apply. The photometric stability of 3 Eatlas represented perhaps its most unsettling characteristic, a flat-like curve that stretched across weeks of continuous observation without showing the variations that defined every other small body in the known universe. Dr. Rachel Park at Palomar Observatory had monitored the object's brightness with obsessive precision, accumulating thousands of measurements that all told the same impossible story. 3 Eatlas wasn't tumbling, or if it was doing so in ways that violated everything astronomers understood about rotational dynamics. Every asteroid, every comet, every fragment of cosmic debris larger than a dust grain rotates. It's a fundamental consequence of formation physics, collision history, and the asymmetric forces that act on irregular bodies in space. This rotation creates predictable brightness variations as different faces of the object reflect sunlight toward Earth. The period, amplitude, and shape of these variations reveal crucial information about size, shape, and surface properties. But 3 Eatlas offered only silence where there should have been a clear rotational signature. The high-precision photometry pushed instrumental capabilities to their limits. Dr. Park used differential techniques, comparing 3 Eatlas to stable reference stars in the same field, correcting for atmospheric variations, telescope systematics, and every source of noise that could mask rotational modulation. The final processed light curves achieved millimagnitude precision, sensitive enough to detect variations of less than 0.1% in brightness. Still, the line remained flat, as constant as the laws of physics that said it shouldn't be. 3 explanations competed for acceptance, each carrying implications that challenged fundamental assumptions. The first proposed that 3 Eatlas was rotating extremely slowly, with a period exceeding the entire observational baseline, but such slow rotation would be unprecedented for an active comet. Outgassing creates torques that spin up cometary nuclei, making slow rotation unstable over time. If 3 Eatlas had somehow achieved near-zero rotation, the first asymmetric jet should have destroyed this delicate balance. The second explanation required the rotational axis to point directly at Earth, eliminating the cross-sectional changes that create brightness variations. The geometric probability of such alignment was approximately 1 in 10,000, assuming random orientation. But even this unlikely scenario failed to explain the complete absence of variations. Unless the nucleus was perfectly spherical, some modulation should appear from surface irregularities or albedo variations. The silence suggested a uniformity that nature doesn't produce. The third possibility was the most troubling. 3I Atlas might be actively controlling its apparent brightness, maintaining constant luminosity through mechanisms that transcended simple reflection of sunlight. This wasn't a scientific hypothesis, so much as an acknowledgement that the observations defied natural explanation. Some researchers had begun calculating what would be required for active stabilization, though these calculations remained in private notebooks rather than published papers. The implications for nuclear structure were profound. Without rotational modulation, determining the object's true shape became impossible. It could be spherical, unlikely as that seemed. It could be elongated, but rotating polon. It could be irregular, but covered in material of perfectly uniform reflectivity. Each possibility was improbable. Together, they formed a set of explanations that satisfied no one. The missing rotation also complicated activity analysis. Cometary jets typically pulse with nuclear rotation, creating periodic variations in gas production that reveal active regions and surface geology. But 3I Atlas's gas emission remained as constant as its brightness, suggesting either uniform activity across the entire surface or regulation mechanisms that smoothed natural variations. The enormous CO2 cloud maintained steady emission rates that didn't correlate with solar heating, distance, or any other observable parameter. Dr. Park had attempted to detect higher-order variations that might reveal complex rotation states. Some asteroids exhibit non-principal axis rotation, tumbling chaotically through space in patterns that create complicated light curves. Advanced Fourier analysis searched for these signatures in the photometric data, finding nothing but noise at the measurement threshold. If 3I Atlas was tumbling complexly, it was doing so in ways that produced no optical signature. The rotational mystery connected to other anomalies in disturbing ways. The stable brightness, despite massive outgassing, suggested mass loss wasn't affecting the object's dynamics as it should. The constant emission, despite changing solar distance, implied thermal regulation beyond simple ice sublimation. The flat light curve, despite violent activity, pointed towards structure or composition, unlike anything in our catalogue of solar system objects. The thermal behavior of 3I Atlas, mapped by the James Webb Space Telescope's mid-infrared instruments throughout August and September 2025, revealed temperature patterns that Dr. Thomas at the Space Telescope Science Institute could only describe as thermodynamically impossible. The object's surface temperatures didn't follow the inverse square law that governed every other body in the solar system, instead maintaining mysterious plateaus that suggested internal heat sources or exotic thermal properties beyond current understanding. The initial thermal measurements seemed reasonable enough. At 3.5 astronomical units from the Sun, 3I Atlas showed surface temperatures around 140 Kelvin, cold enough for CO2 ice stability, but warm enough for sublimation to begin. But as the object moved closer to the Sun, the temperature evolution diverged from all predictions. Instead of warming smoothly, proportional to decreasing solar distance, the temperature increased in discrete steps, plateauing at specific values that had no obvious physical significance. The first plateau occurred at 152 Kelvin, where 3I Atlas's surface temperature remained constant, despite continuing to approach the Sun. This temperature didn't correspond to any phase transition in known ices. It wasn't the sublimation point of CO2, water, or any common volatile. The object maintained this temperature for nearly 2 weeks, as if regulated by an internal thermostat that refused to allow further warming. When the temperature finally increased, it jumped rapidly to 168 Kelvin, where it established another plateau. This pattern continued throughout the approach to perihelion, creating a stepped temperature profile that resembled engineered thermal management more than natural equilibrium. Each plateau lasted days to weeks, punctuated by rapid transitions that occurred over hours. No combination of thermal inertia, heat capacity, or conductivity could explain such behavior. The spatial temperature distribution across 3I Atlas's visible surface added another layer of mystery. JWST's spatial resolution wasn't sufficient to map the nucleus directly, but it could measure temperature variations across the inner coma. These measurements revealed hotspots that didn't correlate with solar illumination angles. Some regions maintained temperatures above 200 Kelvin even when facing away from the Sun, suggesting internal heat sources that transcended simple solar warming. Dr. Chen's thermal models incorporated every possible heat source and sink: solar radiation, sublimation cooling, radiative emission, even exotic processes like crystallization of amorphous ice that could release latent heat. No combination of these mechanisms could reproduce the observed temperature plateaus. The models either predicted smooth temperature curves or chaotic variations, never the regulated steps that 3I Atlas displayed. The infrared spectroscopy revealed additional anomalies in the thermal emission spectrum. Planck's law dictates that objects at specific temperatures emit radiation with characteristic spectral shapes. But 3I Atlas's emission showed subtle deviations from blackbody curves, as if certain wavelengths were being selectively absorbed or emitted. The deviations were small, barely above measurement uncertainty, but consistent across multiple observations. The correlation between temperature and activity provided the most puzzling data point. Normally, cometary outgassing increases exponentially with temperature as more heat drives more sublimation. But 3I Atlas's CO2 production remained nearly constant across the temperature plateaus, increasing only during the rapid transitions between stable states. It was as if the object was deliberately regulating its gas release independent of thermal conditions. Some researchers proposed that 3I Atlas might contain phase change materials that absorbed heat at specific temperatures, creating the observed plateaus. But the temperatures didn't match any known materials, and the heat capacity required to maintain plateaus for weeks exceeded what the object's mass could reasonably contain. The energy budget simply didn't balance using conventional physics. The temporal evolution of thermal anomalies showed increasing deviation from natural behavior as 3I Atlas approached the Sun. Early observations in July had shown approximately normal thermal behavior, following expected heating curves within measurement uncertainty. But each week brought new violations of thermodynamic expectations, as if the object was revealing capabilities it had kept hidden at greater solar distances. The implications for internal structure were profound. Either 3I Atlas contained heat sources beyond solar warming, possibly radioactive decay, or chemical reactions we didn't understand, or it possessed thermal regulation mechanisms that actively controlled temperature. Both possibilities suggested complexity beyond what natural formation processes could produce. The object wasn't just a frozen fragment of another planetary system. It was something that managed its own thermal environment through unknown means. The conference room at the Jet Propulsion Laboratory had witnessed countless scientific debates, but the gathering on September 15, 2025, carried an unusual tension. Dr. Maria Santos had assembled the world's leading cometary scientists to systematically evaluate every natural explanation for 3I Atlas's behavior. 4 hours later, they had methodically demolished each hypothesis, leaving behind a vacuum where understanding should have been. The radiation processing hypothesis had seemed most promising. During millions of years in interstellar space, cosmic rays could theoretically alter surface chemistry, creating exotic compounds that might explain the CO2 dominance. Dr. James Liu from the University of Tokyo had spent weeks bombarding ice samples with particle beams, attempting to reproduce 3I Atlas's spectral signatures. His results were unequivocal. Radiation processing created complex organics and depleted hydrogen, but it couldn't produce the observed 8:1 CO2 to water ratio. The physics of molecular destruction and formation simply didn't allow such extreme selective preservation. The fragmentation model faced even greater challenges. If 3I Atlas was a collection of smaller bodies rather than a single nucleus, it could theoretically maintain the vast CO2 cloud through distributed sublimation. But fragmentation should produce detectable signatures, multiple brightness peaks, irregular coma morphology, variations in velocity dispersion among the fragments. High-resolution imaging from Hubble and ground-based adaptive optics showed none of these features. The object remained stubbornly singular in every observation. Dr. Santos had personally championed the exotic formation environment hypothesis. Perhaps 3I Atlas formed in a protoplanetary disk with radically different chemistry than our solar system, enriched in carbon and depleted in oxygen through processes we hadn't encountered. But stellar nucleosynthesis models place strict limits on possible chemical variations. No realistic combination of stellar mass, age, and metallicity could produce precursor materials that would condense into the observed composition. The periodic table was the same throughout the galaxy. The subsurface ocean model had emerged from studies of Saturn's moon Enceladus, where liquid water beneath an icy crust drives geyser activity. Could 3I Atlas harbor internal liquid reservoirs that regulated its outgassing? The energy requirements killed this hypothesis immediately. Maintaining liquid water at 3A Atlas's distance from the Sun would require internal heat sources exceeding what radioactive decay could provide in such a small body. The thermodynamics were insurmountable. Phase transition theories proposed that 3I Atlas contained exotic ices that underwent structural changes at specific temperatures, potentially explaining the thermal plateaus and regulated emission. Researchers had examined every known ice polymorph, from crystalline to amorphous forms, including hypothetical high-pressure phases that might form in large planetary interiors. None showed phase transitions at the observed temperatures. The plateaus remained unexplained by any known material science. The gravitational disruption scenario suggested that 3I Atlas had recently passed close to a massive object, perhaps a planet or star, that had restructured its interior and triggered unusual activity. But the trajectory analysis showed no recent close encounters. The object's path through space had been lonely and undisturbed for at least millions of years, probably much longer. Whatever was causing its behavior had been present since long before it entered our detection range. Each failed explanation added weight to an uncomfortable truth that none of the assembled scientists wanted to voice directly. Natural processes, at least those currently understood by human science, couldn't account for 3I Atlas's collection of anomalies. Individual mysteries might have conventional explanations, but the combination of impossible chemistry, extended emission, thermal regulation, and rotational stability formed a pattern that transcended known physics. Dr. Santos concluded the meeting with a statement that would later prove prophetic. We're not dealing with an object that challenges our models. We're dealing with something that exists outside our models entirely. Either we're missing fundamental physics, or... She didn't finish the sentence. Everyone in the room understood the implication. The natural explanation wasn't just failing, it was becoming less probable with each new observation. October 29, 2025, would mark perihelion for 3I Atlas, the moment of closest approach to our Sun, when temperatures would peak and activity should reach maximum intensity. Dr. Angela Rodriguez at the Solar Dynamics Observatory had calculated the exact timing. 1433 UTC, when the visitor would pass within 130 million miles of our star. It would also mark the beginning of humanity's blindness, a 60-day period when the most crucial phase of 3I Atlas's journey would be completely hidden from Earth's view. The solar conjunction represented a cosmic conspiracy of geometry. As 3I Atlas swung around the Sun, Earth's orbital position placed our star directly between us and the visitor. Every telescope on Earth, every orbital observatory except those at the Sun-Earth L4 and L5 Lagrange points, would be unable to observe the object. The Sun's overwhelming glare would render 3I Atlas invisible, just when its behavior might reveal the most about its true nature. The Mars Reconnaissance Orbiter offered the only hope for observations during this critical period. On October 3rd, 3I Atlas would pass within 29 million kilometers of Mars, close enough for the high-rise camera to potentially capture detailed images. Dr. Rodriguez had worked with the MRO team to calculate optimal observation windows, accounting for the spacecraft's orbital mechanics and pointing constraints. They would have 3 opportunities, each lasting less than 20 minutes, to glimpse the visitor during Earth's blind period. But even the Mars observations came with severe limitations. MRO's instruments were designed for studying the Martian surface, not tracking fast-moving interstellar objects. The relative velocity between Mars and 3I Atlas would create motion blur in long exposures. The phase angle, the Sun object observer geometry, would be unfavorable for studying coma morphology. At best, they might capture a few pixels of smeared light that confirmed the object still existed. The October blindness meant missing critical evolutionary phases. Perihelion passage often triggers dramatic changes in comets. Fragmentation events as thermal stress cracks the nucleus, explosive outbursts as fresh volatiles become exposed, changes in rotation state as jet forces create torques. For 3I Atlas, with its already anomalous behavior, Perihelion might reveal whether its strange properties resulted from exotic composition or something else entirely. But humanity would be forced to watch the opening acts and the finale while missing the climax. Dr. Rodriguez had proposed an ambitious solution, repositioning one of Earth's solar observation satellites to monitor 3I Atlas during conjunction. The Solar and Heliospheric Observatory, SOHO at the L1 Lagrange point, could theoretically track the visitor as it passed near the Sun. But SOHO's instruments were optimized for studying solar corona, not faint comets. The technical challenges of reprogramming the spacecraft for this unprecedented observation proved insurmountable in the available time. The data gap would create fundamental uncertainties in understanding 3I Atlas's behavior. Without continuous monitoring through perihelion, scientists couldn't determine whether the CO2 emission remained constant or varied with temperature. They couldn't detect any fragmentation or structural changes. Most frustratingly, they couldn't measure any non-gravitational accelerations that might emerge from asymmetric outgassing at peak activity. The most scientifically valuable portion of the encounter would pass unwitnessed. Some researchers had begun calling it the perfect occlusion, noting how precisely the conjunction aligned with perihelion. The probability of such alignment was roughly 1 in 30 for a random trajectory. Not impossible, but unfortunate enough to fuel speculation that the timing wasn't entirely coincidental. If someone wanted to hide something about 3I Atlas's behavior, arranging for solar conjunction during perihelion would be an effective method. The approach to conjunction already showed concerning signs. In late September, as 3I Atlas disappeared into twilight glare, the final observations detected unexpected brightness variations. After months of photometric stability, the object suddenly showed fluctuations that might indicate structural changes or varying activity. But before these variations could be properly characterized, the visitor vanished behind the Sun's brilliance, taking its secrets into a 2-month hiding place where human instruments couldn't follow. The combined spectroscopic data from the world's most powerful telescopes painted a chemical portrait of 3I Atlas that Dr. Susan Park at Caltech could only describe as deliberately impossible. The absorption and emission features detected across ultraviolet, visible, and infrared wavelengths didn't match any combination of known materials, suggesting either chemistry from an environment unlike anything in our galaxy or materials that shouldn't exist, according to current understanding of molecular physics. The carbon dioxide signature that dominated the infrared spectrum showed isotopic ratios that defied stellar nucleosynthesis models. The C13 to C12 ratio, measured with painstaking precision by JWST, fell outside the range that any known stellar process could produce. Too enriched to come from primordial material, too depleted to result from standard stellar fusion. The isotopes suggested processing through pathways that theoretical chemistry hadn't predicted. But the truly impossible features appeared in the 2.7 to 3.1 micron region, where organic molecules typically revealed their presence through characteristic CH stretch vibrations. 3I Atlas showed absorption features in this range, but they were shifted to wavelengths that didn't correspond to any known organic compound. The shifts were too large for simple temperature or pressure effects. They suggested molecular bonds with strength and geometry that shouldn't be stable under any natural conditions. Dr. Park had assembled a team of theoretical chemists to explore exotic explanations. Could the unusual features result from clathrate structures where molecules were trapped in ice cages that modified their vibrational frequencies? Laboratory experiments with every conceivable clathrate combination failed to reproduce the observations. Could long-chain carbon molecules, similar to those found in interstellar space but with unusual branching patterns, create the anomalous signatures? Quantum chemistry calculations showed such molecules would spontaneously decompose. The metallic signatures added another layer of impossibility. Weak features in the visible spectrum suggested the presence of metals, but not in familiar forms. Iron, nickel, and magnesium appeared to be present, but their spectral lines were broadened and shifted in ways that suggested they were incorporated into complex structures rather than existing as simple salts or oxides. Some researchers proposed that 3I Atlas might contain metallic hydrogen or other exotic phases that required pressures found only in planetary cores. The most troubling discovery came from high-resolution spectroscopy aimed at detecting simple molecules like water, ammonia, and methane. These substances should produce forest of narrow absorption lines that revealed temperature, pressure, and velocity information. But 3I Atlas's spectrum in these regions was almost artificially clean, showing only the broadest features while lacking the fine structure that characterized natural molecular spectra. It was as if something was suppressing or smoothing the spectral signatures. Polarimetry measurements revealed that light reflected from 3I Atlas was partially polarized in patterns that changed with rotational phase, despite the photometric brightness remaining constant. This suggested surface structures with organized geometry, perhaps crystalline faces, or aligned materials that reflected light preferentially in certain directions. But the polarization patterns didn't match any crystal structure known to mineralogy. The angles and intensities suggested artificial organization rather than natural crystallization. The near-infrared contained the most enigmatic feature, a broad absorption complex centered at 1.65 microns that had no explanation whatsoever. The feature was strong, consistent across multiple observations, and completely absent from any spectral database. It didn't match water, carbon dioxide, organics, minerals, or any combination thereof. Some researchers had begun calling it the impossible band, a spectral signature that seemed designed to demonstrate that 3I Atlas contained something beyond current human knowledge. Temporal evolution of the spectra provided the final impossibility. As 3I Atlas approached the Sun, its spectrum should have shown predictable changes as temperature increased and different volatiles became active. Instead, entirely new spectral features appeared and disappeared without correlation to temperature or distance. A strong emission line at 4.3 microns appeared for exactly 3 days in mid-September, then vanished completely. A series of absorption features in the visible emerged gradually over 2 weeks, then suddenly sharpened as if activated by crossing some threshold. The accumulated spectroscopic anomalies forced an uncomfortable conclusion. Either 3I Atlas contained materials processed through unknown physics, or its spectrum was being modified by mechanisms that transcended simple molecular absorption and emission. Dr. Viktor Petrov at the European Space Agency spent 3 months attempting to trace 3I Atlas back to its origin, using the most sophisticated orbital dynamics software ever developed. His models incorporated gravitational influences from every major mass in the galaxy, stellar encounters, spiral arm passages, and even dark matter distributions. The result was a trajectory that pointed nowhere, a path through space that seemed to begin in emptiness between the stars, as if 3I Atlas had materialized from vacuum rather than being ejected from a planetary system. The velocity vector provided the first clue that something was fundamentally wrong with 3I Atlas's origin story. Its motion relative to the local standard of rest, the average motion of stars in our galactic neighborhood, was 61 kilometers per second. This placed it kinematically with the thick disk population, stars that formed 8 to 12 billion years ago. But the precise vector didn't match any known stellar stream, moving group, or cluster that could have been its birthplace. Backward integration of the orbit should have revealed a closest approach to some star system in the past, the gravitational encounter that ejected 3I Atlas into interstellar space. Dr. Petrov's models examined every star within 300 light-years, accounting for their proper motions and calculating when and where their paths might have crossed 3I Atlas's trajectory. The search found no convincing candidates. Every potential source star required impossibly precise ejection velocities or trajectories that violated conservation of energy. The galactic orbit itself was problematic. Objects ejected from planetary systems should follow predictable paths through the galaxy's gravitational field, oscillating above and below the galactic plane while orbiting the center. But 3I Atlas's reconstructed path showed anomalies, as if it had experienced accelerations that couldn't be explained by gravity alone. The deviations were subtle, barely detectable given observational uncertainties, but consistent across multiple independent analyses. Statistical analysis made the problem worse. The galaxy contains roughly 400 billion stars, and models suggested that each system ejects numerous small bodies during planetary formation. The interstellar medium should be filled with such objects, following a predictable distribution of velocities and trajectories. 3I Atlas fell far outside this distribution, moving too fast and from the wrong direction to fit natural ejection scenarios. It was like finding a river flowing uphill. Dr. Petrov explored increasingly exotic scenarios. Could 3I Atlas have been accelerated by a supernova explosion? The energy was sufficient, but no supernova remnants aligned with the trajectory. Could it have been ejected from a binary star system undergoing mass transfer? The orbital dynamics didn't match. Could it represent material from the galactic halo that had fallen into the disk? The chemistry was wrong for such ancient metal-poor populations. The age paradox compounded the origin problem. If 3I Atlas truly came from the thick disk population, it had been traveling for billions of years. The probability of such an ancient object arriving at Earth precisely when humans had developed technology to detect it was infinitesimally small. Either the galaxy was filled with such objects, making their rarity in our observations puzzling, or 3I Atlas's arrival was somehow targeted rather than random. Some researchers had begun investigating whether 3I Atlas might be following a powered trajectory rather than a ballistic one. If the object could modify its velocity, even slightly, over millions of years, it could erase the kinematic signatures that would reveal its origin. The energy requirements for such prolonged acceleration were staggering, but the alternative was accepting that 3I Atlas had no identifiable source appearing in our solar system without a comprehensible history. The proper motion measurements added final confirmation of the mystery. As Earth orbited the Sun, our changing perspective should have revealed 3I Atlas's motion against background stars with increasing precision. These measurements, accurate to micro-arc seconds, confirmed the hyperbolic trajectory, but revealed tiny inconsistencies with pure gravitational motion. The object seemed to be adjusting its path in real time, making minute corrections that accumulated into measurable deviations from predicted positions. Dr. Petrov's final report concluded with unusual candor for a scientific document. The kinematic history of 3I Atlas cannot be reconstructed using known physics and observed stellar positions. Either our understanding of galactic dynamics is fundamentally flawed, or this object's trajectory has been influenced by non-gravitational forces operating over geological timescales. Both possibilities require us to reconsider basic assumptions about interstellar objects and their origins. The Transiting Exoplanet Survey Satellite, TESS, wasn't designed to study comets. Its mission focused on detecting planets around distant stars through subtle brightness variations. But when Dr. Helen Chang at MIT reviewed archival data from early 2025, she discovered something that challenged fundamental assumptions about cometary physics. TESS had detected brightness variations from 3I Atlas when it was still beyond Jupiter's orbit, at distances where frozen volatiles should remain locked in perpetual deep freeze. The implications were staggering. At 5.2 astronomical units from the Sun, where TESS first detected activity, the equilibrium temperature would be approximately 125 Kelvin, far below the sublimation point of water ice and barely warm enough for carbon dioxide to begin sublimating under ideal conditions. Yet the photometric signatures clearly showed variability consistent with active outgassing, as if 3I Atlas was responding to heat sources that shouldn't exist at such distances. Dr. Chang's team reprocessed the TESS data multiple times, searching for instrumental artifacts or analysis errors that might explain the impossible observations. The satellite's precision photometry, capable of detecting brightness changes of less than 0.01%, had captured subtle fluctuations in 3I Atlas's light curve that began when the object was farther from the Sun than any comet should show activity. The variations weren't random noise, they showed periodicity and structure suggesting genuine physical processes. The distance-activity relationship in comets follows well-understood physics. Solar radiation decreases with the square of distance, providing 4 times less energy at twice the distance. Water ice typically begins sublimating around 3 astronomical units from the Sun. Carbon dioxide can become active slightly farther out, perhaps at 4 astronomical units under favorable conditions. But activity at 5.2 astronomical units suggested either unprecedented volatile compositions or energy sources beyond solar heating. Laboratory experiments attempted to identify supervolatile compounds that might explain the distant activity: nitrogen ice, carbon monoxide, even exotic species like methane or ammonia were tested under conditions simulating 3I Atlas's environment. None could produce the observed activity levels at such distances without requiring unrealistic abundances or surface areas. The physics of sublimation placed hard limits on what solar heating alone could achieve. The spectroscopic follow-up revealed even greater mysteries. When large telescopes examined 3I Atlas at these extreme distances, they detected not just generic activity, but specific molecular emissions. The carbon dioxide signature was already present, though weaker than during closer approach. More puzzling, there were hints of emissions that didn't correspond to any expected volatile species. Spectral features that suggested unknown processes were already operating while the object should have been dormant. Dr. Chang proposed that 3I Atlas might contain radioactive heat sources, similar to the radioisotope thermoelectric generators that power deep space missions. Natural radioactive decay could provide energy independent of solar distance. But the isotopes required for significant heating, primarily aluminum-26 or iron-60, have short half-lives compared to 3I Atlas's presumed age. Any primordial radioactive material should have decayed to insignificance billions of years ago. Alternative energy sources seemed even less plausible. Chemical reactions might provide temporary heat, but couldn't sustain activity over the observed timescales. Crystallization of amorphous ice releases energy, but requires specific temperature triggers that hadn't been reached. Magnetic field interactions with the solar wind were too weak at such distances. Every proposed mechanism failed to account for the magnitude and duration of the observed activity. The temporal evolution of distant activity showed patterns that defied simple explanations. Instead of gradually increasing as 3I Atlas approached the Sun, the activity showed step functions, suddenly intensifying at specific heliocentric distances that didn't correspond to any volatile sublimation temperatures. It was as if the object was responding to distance thresholds, rather than continuous solar heating, activating systems based on position rather than temperature. The early activity detection forced a fundamental question. If 3I Atlas was already active beyond Jupiter's orbit, how long had it been active before entering our detection range? Had this object been outgassing during its entire interstellar journey, somehow maintaining volatile reserves across billions of years? Or had something triggered its activation as it approached our solar system? Some proximity sensor that detected the Sun's presence and began preparing for perihelion passage? Neither possibility fit within conventional cometary science. The Allen Telescope Array in Northern California had been listening since the moment 3I Atlas was discovered, its 42 radio dishes focused with unprecedented attention on a single point of light racing through the solar system. Dr. Michael Torres, leading the SETI Institute's observation campaign, had configured the array to detect any electromagnetic emission from the visitor across a frequency range spanning from 1 to 10 gigahertz. After 3 months of continuous monitoring, the result was unequivocal and deeply troubling. Absolute radio silence. This silence wasn't what astronomers expected from an object showing such vigorous activity. Comets typically produce radio emissions through multiple mechanisms. Molecular transitions in the coma generate spectral lines at specific frequencies. Plasma interactions between sublimated gas and the solar wind create broadband noise. Even dust particles can scatter and emit radio waves under certain conditions. Yet 3I Atlas, despite its enormous CO2 cloud and evident activity, produced no detectable radio signature whatsoever. The sensitivity of the search was extraordinary. The Allen array could detect signals as weak as 10 to the -27 watts per square meter per hertz, equivalent to the power of a cell phone transmission from beyond Pluto. The integration time stretched to hours, then days, building up signal-to-noise ratios that should have revealed even the faintest natural emissions. Sophisticated algorithms searched for periodic signals, broadband noise, narrowband carriers, anything that would indicate electromagnetic activity. The spectrum remained empty. Dr. Torres explored increasingly exotic explanations for the radio silence. Perhaps 3I Atlas's emissions were beamed in directions away from Earth, creating a radio shadow where we happen to be positioned. But the object's passage through different geometries relative to Earth should have revealed some emission angles. Perhaps the emissions were at frequencies outside the search range, in the millimeter or submillimeter bands, where molecular transitions might lurk. But follow-up observations with ALMA found nothing there either. The absence of plasma emissions was particularly puzzling. When cometary gas interacts with the solar wind's charged particles, it creates a bow shock that generates radio waves through well-understood processes. This mechanism doesn't depend on composition or temperature. It's a fundamental consequence of charged particle dynamics. The fact that 3I Atlas showed no plasma emissions suggested either its gas wasn't becoming ionized, which contradicted the UV observations, or something was suppressing the radio generation mechanism. Some researchers proposed that 3I Atlas might be surrounded by a Faraday cage-like structure that blocked radio emissions from escaping. Such a configuration would require a shell of conductive material, precisely arranged to create an electromagnetic shield. The idea seemed absurd for a natural object, yet it would explain the radio silence while permitting the observed optical and infrared emissions. The implications of such a structure were carefully avoided in published papers. The silence became more troubling when compared to other interstellar visitors. While Oumuamua and Borisov hadn't produced strong radio emissions, they had shown the weak signals expected from their modest activity levels. 3I Atlas, with its extraordinary CO2 production and extended coma, should have been radio loud by comparison. Instead, it was quieter than objects a fraction of its activity level, as if deliberately maintaining electromagnetic silence. Dr. Torres had arranged for coordinated observations with radio telescopes worldwide. The Very Large Array in New Mexico, the Parkes Observatory in Australia, and the Effelsberg Telescope in Germany all confirmed the non-detection. The global radio silence wasn't an artifact of location or equipment. It was a genuine property of 3I Atlas that transcended conventional explanation. The temporal monitoring revealed no variations in the radio silence. As 3I Atlas approached the Sun and its activity increased, the radio spectrum remained empty. Even during reported brightness fluctuations that suggested structural changes or outburst events, no electromagnetic pulse accompanied the optical variations. It was as if the object was actively suppressing radio emissions that should naturally accompany its observed behavior. The philosophical implications of the radio silence divided the scientific community. Some saw it as evidence that 3I Atlas was genuinely exotic, perhaps containing materials or structures that prevented normal radio emission processes. Others viewed the silence itself as suspicious, too perfect and complete to be natural. The absence of expected signals had become a signal itself, a negative space in the data that spoke louder than any detection might have. The fundamental equation was simple enough that any astronomy student could solve it. Given an object's brightness and distance, calculate its size, assuming reasonable reflectivity. But when Dr. David Lee at Palomar Observatory applied this basic relationship to 3I Atlas, the results made no physical sense. The object was simultaneously too bright for its maximum possible size and too small for its observed activity, creating a paradox that challenged the basic physics of how light interacts with matter. The brightness measurements were unambiguous. Multiple observatories had tracked 3I Atlas's apparent magnitude since discovery, accounting for distance, phase angle, and solar illumination. The integrated brightness of nucleus and coma suggested a reflecting surface area that, assuming typical cometary albedo of 4%, would require a nucleus at least 15 kilometers across. But Hubble's resolution constraints placed an upper limit of 5.6 kilometers on the nuclear diameter. The discrepancy factor of 3 couldn't be explained by measurement error. Dr. Lee explored every possible resolution to the paradox. Perhaps 3I Atlas had an unusually high albedo, reflecting more light than typical comets. But achieving the observed brightness with a 5-kilometer nucleus would require an albedo exceeding 35%, more reflective than fresh snow and completely inconsistent with the spectroscopic evidence for dark, carbon-rich surface materials. The absorption features in the spectrum demanded low albedo, while the brightness demanded high albedo. The alternative was even more troubling. If the albedo was indeed low, as spectroscopy suggested, then 3I Atlas must be larger than Hubble's resolution limit. This would require the nucleus to somehow remain unresolved despite its size, perhaps by maintaining perfect spherical symmetry or possessing surface properties that prevented normal light scattering. Either possibility suggested characteristics that natural formation processes don't produce. Polarimetry measurements deepened the paradox. Light reflected from rough surfaces becomes partially polarized in predictable ways that depend on composition and texture. 3i Atlas showed polarization signatures consistent with fine-grained, dark material similar to carbonaceous asteroids. Such materials typically have albedos below 5%, making the brightness paradox even more acute. The object was reflecting light, like a dark surface, while somehow producing the brightness of a mirror. Dr. Lee's team investigated whether fluorescence might contribute to the anomalous brightness. Some materials can absorb ultraviolet radiation and re-emit it at visible wavelengths, effectively increasing their apparent brightness. But fluorescence produces characteristic spectral signatures that weren't present in 3i Atlas's spectrum. The light was pure reflection, not re-emission, yet the magnitude of reflection exceeded what the surface area could provide. The phase function, how brightness varies with observation angle, provided another confusing data point. Most small bodies show strong phase dependence, brightening dramatically when viewed at opposition and dimming at high phase angles. 3i Atlas showed an unusually flat phase function, maintaining nearly constant brightness regardless of viewing geometry. This suggested either unusual surface properties or internal light sources that compensated for geometric effects. Temporal variations in the brightness paradox proved even more puzzling. As 3i Atlas approached the Sun, its brightness increased faster than the inverse square law predicted. The object wasn't just reflecting more light due to proximity, it was becoming intrinsically brighter through unknown mechanisms. The brightening didn't correlate with increased activity or coma development, ruling out simple explanations based on growing dust clouds. Some researchers had begun calculating the requirements for artificial illumination that could resolve the paradox. If 3i Atlas possessed internal light sources supplementing reflected sunlight, the power requirements would be modest by human standards, perhaps a few megawatts. But maintaining such power generation across interstellar distances and geological timescales exceeded any known technology. The calculation remained in private notebooks, too speculative for publication. The size-brightness paradox connected uncomfortably with other anomalies. The extended CO2 cloud suggested a large active surface area. The constant rotation implied a symmetric shape. The thermal plateaus indicated internal heat sources. Each anomaly alone might have conventional explanations, but together they painted a picture of an object that transcended simple categories of comet or asteroid. Dr. Lee's final analysis concluded with unusual honesty. 3i Atlas exhibits photometric properties that cannot be reconciled with its physical constraints, using conventional models of light scattering and reflection. Either our understanding of fundamental optical physics is incomplete, or this object possesses characteristics that natural formation processes cannot produce. The anti-solar tail of 3i Atlas, finally detected by the Gemini South Telescope in late August 2025, should have been a triumphant confirmation of normal cometary behavior. Instead, it became yet another impossibility in the growing catalogue of anomalies. Dr. Rachel Kim at the Gemini Observatory had analyzed thousands of comet tail images throughout her career. But 3i Atlas's dust dynamics violated every model she had ever used to understand how particles behave in the solar system's gravitational and radiation environment. The tail was there, but barely. Where comparable comets at similar distances produced dramatic dust tails stretching millions of kilometers, 3i Atlas showed only a faint, stubby appendage extending perhaps 50,000 kilometers from the nucleus. The weakness wasn't due to low dust production. The coma clearly contained substantial solid particles. Instead, the dust seemed to resist the forces that should sweep it into a prominent tail. Solar radiation pressure, the force that pushes dust particles away from the sun, operates according to well-understood physics. Particles smaller than a micron are blown away rapidly. Particles between 1 and 100 microns are pushed more gently, forming the curved tails that make comets spectacular. Particles larger than a millimeter are barely affected, remaining near the nucleus. 3i Atlas's dust appeared to consist entirely of this largest category, defying models of how cometary dust forms. Dr. Kim's analysis of tail morphology revealed additional impossibilities. The dust wasn't following Keplerian orbits modified by radiation pressure, the standard behavior that creates the curved synchrone syndine patterns in normal comet tails. Instead, the particles seemed to maintain nearly constant positions relative to the nucleus, as if held by forces beyond gravity and radiation. The tail didn't curve, didn't spread, didn't evolve in the ways that dust dynamics demanded. Spectroscopic analysis of the dust revealed unusual properties that might partially explain its behavior. The particles showed absorption features, suggesting they were aggregates of smaller grains bound together by unknown mechanisms. But even large aggregates should eventually disperse under solar heating and radiation pressure. 3I Atlas's dust remained mysteriously cohesive, maintaining structures that should have evaporated in minutes or hours. The color of the dust added another puzzle. Most cometary dust appears reddish due to organic compounds and radiation processing. 3I Atlas's dust was notably gray, almost colorless, suggesting either unusual composition or particle sizes that scattered light differently than expected. The neutral color persisted across different wavelengths, from ultraviolet through near-infrared, defying models of how natural particles interact with light. Polarization measurements of the tail revealed highly organized structure. The dust particles appeared to be aligned, all oriented in similar directions, rather than randomly tumbling as expected. This alignment created polarization patterns that swept across the tail in waves, as if the particles were responding to invisible forces that organized their orientations. No known mechanism could create such alignment in the chaotic environment of a comet's tail. The velocity dispersion of dust particles was anomalously low. In normal comets, dust is ejected at various speeds depending on particle size and ejection location, creating a spread of velocities that broadens the tail over time. 3I Atlas's dust moved in near-perfect synchronization, maintaining tight spatial grouping that suggested either simultaneous ejection with identical velocities or active coordination of particle motion. Dr. Kim attempted to model the dust behavior using magnetohydrodynamic simulations, wondering if electromagnetic forces might explain the anomalies. But 3I Atlas showed no evidence of the magnetic fields required for such effects. The particles weren't metallic enough to respond strongly to magnetism. The solar wind at that distance was too weak to create the observed organization. Every force that might control dust behavior was either absent or insufficient. The temporal evolution of the tail provided the final mystery. As 3I Atlas approached the Sun, the tail didn't grow proportionally with increased activity. Instead, it maintained nearly constant length and brightness, as if regulated by mechanisms that prevented normal tail development. During reported outburst events, when fresh dust should have been ejected into the tail, no corresponding brightening or lengthening occurred. The tail remained stubbornly stable, defying the dynamic behavior that defined every other comet. Some researchers had begun using the term constrained ejector to describe 3I Atlas's dust behavior, carefully avoiding speculation about what might be constraining it. The particles were clearly leaving the nucleus, entering the coma, but then remaining in configurations that natural forces couldn't maintain. It was as if the dust was following rules that transcended conventional physics, organized by principles that human science hadn't yet discovered. December 5, 2025, at 6:42 UTC, 3I Atlas emerged from behind the sun's glare like a cosmic actor returning for a final bow. Dr. Jennifer Walsh at the Keck Observatory in Hawaii had been waiting at her instruments since before dawn, ready to capture the first post-perihelion observations of humanity's most enigmatic visitor. What she saw in those first spectroscopic measurements made her question whether they were looking at the same object that had disappeared behind the sun 2 months earlier. The carbon dioxide emission had intensified beyond all predictions. Where models suggested gradual decrease as the object receded from solar maximum, 3I Atlas blazed with CO2 production that exceeded pre-perihelion levels by a factor of 3. The extended cloud now reached 500,000 kilometers from the nucleus, a volume so vast it could encompass the orbits of Earth and Moon with room to spare. Whatever had happened during solar conjunction had fundamentally altered the visitor's behavior. But it was the new spectral features that truly disturbed the watching astronomers. Lines that hadn't existed before perihelion now dominated entire regions of the spectrum. A strong emission at 3.4 microns, suggested complex hydrocarbons that shouldn't survive at the temperatures 3I Atlas had experienced. A series of narrow absorptions between 7 and 8 microns formed patterns that no molecular database could identify. The object wasn't just active, it was chemically transformed. Dr. Walsh coordinated with observatories worldwide to confirm these impossible observations. The Very Large Telescope in Chile, the Subaru Telescope in Hawaii, and space-based assets all reported identical features. This wasn't instrumental error or atmospheric contamination. 3I Atlas had genuinely changed during its hidden passage around the Sun, emerging with properties that challenged fundamental assumptions about cometary evolution. The nuclear brightness had increased by 2 full magnitudes, far exceeding what the closer solar distance could explain. If the size constraints from Hubble remained valid, this brightness increase required either a dramatic jump in albedo or internal luminosity that transcended reflected sunlight. Some researchers calculated that 3I Atlas was now emitting more light than it received, a thermodynamic impossibility unless energy sources beyond solar radiation were operating. Morphological changes were equally dramatic. The previously symmetric coma now showed distinct jets and streamers, but they didn't behave like normal cometary jets. Instead of expanding and dissipating with distance, these structures maintained coherent forms extending thousands of kilometers from the nucleus. They pulsed with regular periodicity, brightening and dimming on timescales of hours, as if controlled by mechanisms that regulated mass flow with mechanical precision. The December observations revealed that 3I Atlas's rotation had changed. After months of photometric stability, the object now showed clear brightness variations with a period of 47.3 hours. But this wasn't chaotic tumbling induced by outgassing torques. The rotation was perfectly regular, maintaining constant period and amplitude, as if the object had deliberately adjusted its spin state during perihelion passage. Dr. Walsh's team detected something even more unsettling in the high-resolution spectra: emission lines that shifted frequency over time, not from Doppler effects, but as if the molecular transitions themselves were changing. It was as if the fundamental quantum states of molecules in 3I Atlas's coma were being modified by unknown processes. Such behavior violated basic quantum mechanics, yet multiple independent observations confirmed the phenomenon. The polarimetry revealed that reflected light from 3I Atlas now carried information. The polarization angle varied in patterns that weren't random or naturally organized. Some researchers noted that the patterns resembled binary encoding, though attempts to decode any message from the polarization variations yielded only mathematical noise. Still, the organization was undeniable, as if 3I Atlas was modulating its reflected light to carry signals we couldn't interpret. As December progressed toward January, the window for detailed observations narrowed rapidly. 3I Atlas was racing away at over 150,000 miles per hour, growing fainter each night. The December revelation window had provided more questions than answers, showing that perihelion had transformed the visitor in ways that transcended natural explanation. Dr. Margaret, head of statistical analysis at the International Astronomical Union, had spent her career calculating probabilities for astronomical phenomena: supernovae rates, asteroid impact risks, the likelihood of discovering Earth-like exoplanets. But when she compiled the probability calculation for 3I Atlas's combined anomalies occurring naturally in a single object, the number that emerged from her equations was so small, it challenged the meaning of statistical possibility itself. 10 to the power of -47, a probability so minute that it was effectively zero. The calculation began simply enough. What was the probability of an interstellar object having a CO2 to water ratio of 8 to 1? Based on all known cometary chemistry and theoretical models, perhaps 1 in 10,000. Unusual, but not impossible. What about maintaining a gas cloud extending 500,000 kilometers? Given the nuclear size constraints, maybe 1 in 1,000. Still within the realm of statistical possibility. But as Dr. Margaret added each anomaly to her calculation, the probabilities multiplied into increasingly infinitesimal numbers. The rotation that showed no variation for months then suddenly became perfectly periodic. 1 in 100,000. The temperature plateaus that ignored thermodynamic laws. 1 in a million. The spectroscopic features that matched no known chemistry. 1 in 10 million. The trajectory that perfectly threaded Earth's observation window. 1 in 50 million. The mathematical framework Dr. Margaret employed was rigorous, peer-reviewed, and conservative. She used Bayesian analysis to account for observational biases. She incorporated error margins that favored natural explanations. She consulted with experts in each subdiscipline to ensure her probability estimates were generous rather than restrictive. Every analytical choice was made to increase the likelihood of natural occurrence. The final probability still bordered on impossibility. Some colleagues argued that her analysis suffered from the prosecutor's fallacy, inappropriately combining independent probabilities. But Dr. Margaret demonstrated that many of 3I Atlas's anomalies were causally linked. The extended gas cloud related to the unusual chemistry, the thermal regulation connected to the activity patterns. These weren't independent dice rolls, but connected phenomena that made the combined improbability even more significant. The comparison with lottery statistics provided sobering context. The odds of winning a major lottery jackpot were roughly 1 in 300 million. The probability of being struck by lightning twice was about 1 in 9 million. The chance of 3I Atlas's properties occurring naturally was equivalent to winning the lottery 13 times in a row, while being struck by lightning during each drawing. Mathematics had a word for such probabilities: impossible. Dr. Margaret examined whether selection bias could explain the statistical anomaly. Perhaps many normal interstellar objects passed undetected, and we only noticed the weird ones. But this argument failed against 3I Atlas's brightness and activity. The object wasn't marginally detectable, it was surprisingly obvious once discovered. If anything, selection bias should have favored discovering normal objects first, making 3I Atlas's extreme properties even more improbable. The temporal clustering of anomalies added another statistical dimension. If 3I Atlas's strange properties were distributed randomly throughout its passage, coincidence might be plausible. But the anomalies had intensified in perfect correlation with human observational capability. The most extreme features emerged just as our instruments reached maximum sensitivity. The probability of this timing occurring by chance multiplied the already impossible odds by additional factors of thousands. Dr. Margaret's report included a section that would later become infamous in the scientific community. She calculated the probability that 3I Atlas was artificial versus natural, using conservative assumptions that heavily favored natural explanations. Even with these biased assumptions, the Bayesian analysis suggested less than 0.0001% probability of natural origin. The mathematics was essentially stating what many scientists thought but wouldn't say. 3I Atlas couldn't be natural. The institutional response to these calculations was swift and divisive. Some researchers accused Dr. Margaret of sensationalism, arguing that improbable didn't mean impossible. Others praised her courage in following mathematics to its logical conclusion. The debate raged in journal editorials and conference presentations, but nobody could find fundamental errors in her calculations. The numbers stood unchallenged, a statistical verdict that transcended human interpretation. The mission profile that Dr. Robert Zhang presented to NASA's Planetary Science Division on December 15, 2025, was simultaneously brilliant and hopeless. Using every trick of orbital mechanics, leveraging gravitational assists from 3 planets, and pushing propulsion technology to theoretical limits, his team had designed a trajectory that could potentially intercept 3I Atlas in 2031. The only problem was that it required launching a spacecraft that didn't exist using technologies we hadn't invented to achieve velocities that violated the rocket equation's fundamental constraints. The mathematics were merciless. 3I Atlas was now receding at 67 kilometers per second relative to Earth, accelerating away as it climbed out of the Sun's gravity well. To catch up required not just matching this velocity, but exceeding it significantly to allow for reasonable transit time. The delta V budget, the total velocity change needed, came to 95 kilometers per second. For comparison, the Apollo missions to the Moon required only 6 kilometers per second. Dr. Zhang's team had explored every possible approach. Chemical rockets, even using the highest performance propellants, could provide perhaps 15 kilometers per second with staging. Nuclear thermal propulsion might reach 25 kilometers per second. Ion drives could theoretically achieve higher velocities, but would take decades to accelerate to useful speeds. Even hypothetical fusion rockets would struggle to meet the energy requirements for intercepting 3I Atlas within a human lifetime. The gravitational assist strategy offered the only slim hope. By launching toward Jupiter, using its massive gravity to redirect towards Saturn, then performing a powered flyby of the Sun, a spacecraft could theoretically gain enough velocity to catch 3I Atlas. But the alignment of planets required for this trajectory wouldn't occur until 2029, and the spacecraft would need to survive a solar approach within 0.1 astronomical units, 10 times closer than Parker Solar Probe's record-breaking perihelion. The payload constraints were equally restrictive. After accounting for propulsion requirements, the spacecraft could carry perhaps 50 kilograms of scientific instruments. No sample return was possible. The mission would be one way, transmitting data until power failed, or distance made communication impossible. The entire scientific return from humanity's first interstellar intercept would depend on a few hours of flyby observations by instruments weighing less than a typical adult human. Dr. Zhang had also calculated the requirements for a nuclear pulse propulsion mission, despite international treaties banning nuclear explosions in space. Project Orion-style spacecraft could theoretically achieve the necessary velocities by detonating small nuclear devices behind a massive pusher plate. The engineering was theoretically sound, the physics well understood. But the political impossibility of launching hundreds of nuclear weapons into space made this option purely academic. The private space industry offered no solutions either. SpaceX's Starship, Blue Origin's New Glenn, even conceptual vehicles on corporate drawing boards fell short by orders of magnitude. The energy required to intercept 3I Atlas exceeded what chemical rockets could provide, regardless of funding or engineering brilliance. Physics itself had become the enemy, placing fundamental limits on humanity's ability to reach this cosmic visitor. Some researchers proposed waiting for better technology. Perhaps in 20 or 30 years, fusion rockets or antimatter propulsion might make intercept possible. But by then, 3I Atlas would be beyond Neptune's orbit, requiring even more extreme velocities to catch. The window was closing, not in years, but in months. Every day of delay added kilometers per second to the already impossible velocity requirements. The psychological impact on the space science community was profound. Here was the most important astronomical discovery in human history, a visitor that challenged every assumption about the universe, and we were helpless to study it properly. We could only watch through telescopes as it carried its secrets back to interstellar space, a cosmic treasure chest locked forever beyond our reach. Dr. Zhang's presentation concluded with unusual emotion for a technical briefing. We stand at the shore of the cosmic ocean, watching the most important message in a bottle we've ever seen floating away. We have the knowledge to read it, the will to retrieve it, but not the means to reach it. 3I Atlas will leave our solar system unstudied, taking answers to questions that may define humanity's future understanding of our place in the universe. The emergency session of the International Astronomical Union on January 3, 2026, didn't focus on 3I Atlas, which was already fading beyond detailed observation. Instead, Dr. Sarah Mitchell presented statistical models that transformed the visiting interstellar object from a rare cosmic accident into an inevitable regular occurrence. Her analysis of discovery rates, detection capabilities, and population estimates suggested something that chilled the assembled astronomers. 3I Atlas wasn't an ending. It was a beginning. The progression was undeniable. One interstellar visitor in 2017, another in 2019, then 3I Atlas in 2025. The intervals were shortening, but not because space was becoming more crowded. Our detection capabilities were improving, revealing a population that had always been there. Dr. Mitchell's models suggested the solar system hosted 3 to 10 interstellar objects at any given time, most too small or distant to detect with current technology. The Vera Rubin Observatory, finally operational after years of delays, would change everything. Its 8.4-meter mirror and 3.2 gigapixel camera would photograph the entire visible sky every 3 nights, achieving depth and coverage that dwarfed all previous surveys combined. Conservative estimates suggested Rubin would detect 1 interstellar visitor per year. Optimistic projections put the number at 1 per month. The age of interstellar astronomy had truly begun. But Dr. Mitchell's models contained a disturbing implication that she presented with careful scientific detachment. If the anomaly rate observed in our first 3 visitors held constant, approximately 1/3 of future interstellar objects would display properties that challenged natural explanation. Within a decade, we might catalogue 10 to 30 objects like 3I Atlas, each one presenting unique impossibilities that accumulated into an undeniable pattern. The European Space Agency's Comet interceptor mission, scheduled for launch in 2029, had been redesigned specifically for interstellar encounters. Stationed at the L2 Lagrange point, it would wait like a coiled spring, ready to intercept targets of opportunity within months of discovery. But even this preparation might prove insufficient if visitors arrived with the frequency Dr. Mitchell predicted. China announced plans for an even more ambitious program, a constellation of interceptor spacecraft positioned throughout the inner solar system. When the next 3 I-Atlas-like object appeared, multiple spacecraft could approach from different angles, ensuring comprehensive observations regardless of trajectory. The program would cost hundreds of billions of dollars, but the scientific and potentially existential value justified the expense. The radio astronomy community was mobilizing with equal urgency. The square-kilometer array, when completed, would possess sensitivity to detect emissions 1,000 times fainter than current limits. If interstellar visitors were producing electromagnetic signals below current detection thresholds, SKA would find them. The facility was being fast-tracked specifically to be operational before the next anomalous visitor arrived. Dr. Mitchell's presentation included a timeline that nobody wanted to contemplate, but everyone recognized as necessary. Based on discovery rates and increasing anomaly frequencies, she predicted that by 2035, the accumulated evidence for non-natural interstellar objects would reach statistical certainty. The question wouldn't be whether artificial objects were visiting our solar system, but what their presence meant for humanity. The institutional preparations extended beyond pure science. The United Nations Office for Outer Space Affairs was drafting protocols for responding to confirmed artificial objects. Military organizations were gaming scenarios where interstellar visitors showed hostile intent or dangerous capabilities. Philosophy departments were exploring the implications of confirmed non-human intelligence. The entire intellectual infrastructure of human civilization was preparing for a possibility that 3I Atlas had made suddenly real. As January turned to February and 3I Atlas faded below the detection limits of even the largest telescopes, its legacy was already transforming human society. Every major observatory was being modified for rapid response capabilities. Every space agency was developing interceptor missions. Every radio telescope was implementing new search protocols. We were preparing not just for the next visitor, but for the moment when their accumulated presence would force us to confront a truth that 3I Atlas had only hinted at. The universe had been sending us messages, and we were finally learning to read them. The only question was whether we would like what they had to say. As Dr. Mitchell concluded her presentation, she displayed a single image, a projection of discovered interstellar objects over the next decade. The graph curved exponentially upward, each point representing another mystery, another challenge to our understanding, another step toward a revelation that 3I Atlas had begun, but future visitors would complete.